So hi, what's on the agenda for today? I'll be giving a brief introduction. I'll be talking about DBX and microcode, what they are, how they are loaded, and how they are updated. The new continuous integration for them we've developed, and some closing thoughts of ideas for improvements. So hi, I'm Michał Kopeć. I work at FreeMDev. I have been working here for 4 years now. And I primarily work with Coreboot and EDK2, but also heads and some Linux kernel development. Okay, so let's talk about the most critical parts of the boot security, of firmware security. The first and the last components of the firmware trust chain are microcode updates and UEFI DBX respectively. So the first component is microcode, which includes processor level fixes and mitigations for example, Spectre and Meltdown, and they are applied very early by Coreboot. And then we have UEFI Revocation Database, or DBX, which is part of UEFI Secure Boot and revokes compromised binaries, for example, the boot hole exploit and revoked signing certificates that are no longer trusted. The firmware chain of trust is therefore microcode, Coreboot, UEFI, bootloader, and OS. And each stage verifies the next. Our goal is consistent security and timely security. So we have to ensure that critical components such as microcode and DBX are always up to date. Continuous integration helps reduce the risk of oversight in that regard and frees up development resources a little bit. So the solution is automation. The Intel boot process. So I'll talk about how an Intel processor starts and how it relates to the overall boot chain. So the PMC starts executing first when power is applied to the SoC. It then releases CSME or Intel ME management engine, converts security management engine, converts security engine, and many other different names from Reset. CSME has a minute IA processor core that behaves much like a regular 486 processor. The CSME ROM is protected by a fuse that is burned by Intel during production. So essentially, the CSME ROM acts like a 486 BIOS, you could say. CSME maps the ROM boot extensions partition from SPI flash, then the ROM boot extensions, or RBE, verify and load the CSME OS, performs anti-rollback checking, and initialize the secure components. Then we've got RBE, which initiates the bring up phase. Bring up phase initializes services, and then the CPU is finally released from reset. And the CPU starts with loading microcode from the fit table. So it's worth noting that this happens before the BIOS code has even had a chance to start executing. Then, if bootguard is supported, then the CPU loads bootguard ACM from the firmware interface table, which enforces BIOS verification, and then the BIOS is allowed to run. So you can see that there are a lot of steps between powering on and when the BIOS even starts executing. So, microcode. The purpose is to fix security advisories, functional issues like the chip degradation, infamous of Intel Raptor-like processors, and some other errata. They are often essential for basic CPU operations. So, for example, an Intel CPU will not do much useful stuff, probably not even print anything to the serial console, unless microcode is provided via the firmware interface table. OS can also load updates, but firmware level is earlier and more comprehensive, so it protects against more vulnerabilities. An example vulnerability would be Intel SA01139, which is privilege escalation via module input validation. Then we have the UEFI DBX, or revocation list. It's sourced from the UEFI forum or from Microsoft GitHub. We use Microsoft's Git repository for easier automation and for quicker updates. So yeah, while working on this automation, I noticed that the file provided by the UEFI forum is actually older than what Microsoft provides on their GitHub repository. Presumably they updated the GitHub but forgot to update the UEFI forum then. So this highlights why we need a reliable source that we can use. As I just said, microcode DBX revokes signatures of previously approved firmware or software. It's critical for mitigating bootkits like Black Lotus and compromised bootloaders. And revoking certificates is powerful, invalidates any binaries that may be signed by such a certificate. An example vulnerability is Black Lotus, a persistent UEFI bootkit bypassing UEFI secure boot. The automation. We are using GitHub Actions because our code is hosted on GitHub. So this makes it very easy to integrate with our code bases. It has a simple to understand declarative YAML syntax, and it supports a wide range of community actions. So blocks that can be reused for different purposes than the author originally created. And the checks are performed daily. So the automation of microcode update. We first check out the Dasharo and microcode repositories. We compare the microcode submodule revisions, and then we check if they are outdated. And if the microcode is indeed outdated, then the first step, the checking, exits with a code 1. And if it is outdated, then we just update the submodule to the latest version and commit changes via a GitHub action. And that's it. That's pretty much it, the entire workflow. For DBX, the process is very similar. We check out the Dasharo repository and Microsoft Secure Boot repository. We compare the hashes of the DBX files, and again, if outdated, then we update the DBX. We commit changes via a GitHub action and create a pull request, and that's done. It's worth noting that the PRs are not automatically merged. The changes are not fully automatic. They still go through the standard Dasharo review process. So developers have to review the changes and they have to ensure that it indeed works as expected. But the CI isn't, for example, adding some garbage because something changed on the upstream repositories. And we have to test on relevant hardware platforms for that reason. And the commits have to be signed before they are merged into our code repositories. So that has to be done by an actual person as well. The benefits of this are enhanced security. We get regular automated updates that minimize vulnerabilities. We have increased transparency because the repositories are open and the CI workflows are open and the pull requests are publicly available. Users can see the update status and history, and the community can audit our processes and adapt our methods for their purposes, or maybe submit some improvements for us. In contrast, many proprietary firmware solutions are very opaque. The changelogs aren't very verbose compared to our changelogs, which tend to have SBOM, software bill of materials sections, which explain in detail what components you're getting and from where they come. So yeah, in summary, automated checks make Dasharo firmware more secure and more transparent. The automations build user trust and give them the power of knowledge. We hope this makes Dasharo safer and more worthy of our users' trust. And again, the code is open, so feel free to check it out. And if you have any improvements, we would be glad to review them. That's it for my presentation. Do we have any questions? Nothing on the elements on the VPub chat?
Okay, thanks, Michal. Question: updating microcode for fit loading. There is a tight coupling with FSP. Is that automated too?
Again, updating FSP as well?
Yeah. So this is question from Andrew, which is on the matrix.
Okay.
For fit loading, there is a tight coupling with FSP. Is that automated too? I just wondering what kind of coupling. And so yeah, and Michik already kind of tried to discuss it and asking if there is no coupling with FSP currently.
Maybe the new incoming FSP will be like loaded via fit, but that's not yet, I think, ready on any production silicon right now. But Intel was planning like the FSP from reset, right?
Mm-hmm.
So the CPU starts off the bat with the FSP loaded from fit.
Going back to the question of updating the FSP automatically, that is not currently updated because updating the FSP has the risk of breaking a lot of stuff like display, and maybe Codeboot hasn't been adapted for with all the changes to the headers that FSP provides.
Yeah, I guess, but that's very interesting point from Andrew about like maybe that's even more general question about all the binary blobs which are published. Maybe all of them should be somehow, automatically fetched. Yeah, I understand that FSP is not possible because of the headers and potential misconfiguration, but you can imagine that the CI will be more sophisticated. Yeah.
Yeah, maybe.
And then maybe after integration, it will check if there is no kind of regression with that. I to be honest, I also don't know how often FSP is publicly updated. I would say not often. I'm not sure how many FSP release you get per microarchitecture.
So, for example, for Meteor Lake, we haven't had a public client FSP release yet. We have to obtain the FSP manually from Intel and upload it to a public location. So that would be extremely difficult to automate.
Yeah, agree. Yeah, but that's one case. Yeah, I guess like there are other cases. Like I'm guessing like the discussion is only about those which are feasible, not about those which are not feasible.
Okay, sure.
Yeah. So, but do you recall how many FSP updates we get for given microarchitecture?
It's not very often, I think. Let me quickly check the Intel repository.
And there are other blobs like management engine. Like our management engine is also something that we obtain from the source, which is not easily automated. It cannot be easily automated. But on the other side, maybe that's part of the lobbying in the ecosystem. Yeah, like that could be part of complaint which community could take and take to the audience, and maybe someone will hear that. Yeah, so you could publish ME in some reasonably good place, which will help in doing the automated updates instead of doing it that way right now.
Yeah, example of Raptor Lake SFSP, or just only 2 commits updating the FSP blob on the repository. So it's like
Raptor
usually
Lake was released 2 years ago, or
yes, 2 years ago we can say.
so one release per year are on average.
Yeah, and that's it.
And that's it. Probably there will be no more.
There will be no more, probably.
I wonder about Elkhart Lake, because Elkhart Lake got the 15 years life cycle. So the question is how many updates there will be for Elkhart Lake.
The embedded ones have like more frequent updates, those especially which have some IoT. For example, Elkhart Lake has like, I don't know, 1, 2, almost 20 updates throughout 4 years. So it really depends on the segment and the purpose of the microarchitecture, right?
I guess we have 3 minutes left. There are some questions from Demi. Does this mean that the non-automated validation is a problem in and of itself? Non-automated validation. Of course, that is a problem. But does Intel always provide the non-microcode fixes for 3M to ship? Intel does not provide anything for 3M. Like, we are nothing to them, and we are like it's like we are nothing to any silicon vendor. So like non-silicon vendor provides anything to 3M. So 3M can just fetch things from known locations or watch some known locations, which we have access to thanks to some partnership programs. And I guess that's it. I don't know, Michał, Michik and Michał, like if we can add anything to that.
Yeah, we don't even get access to the most crucial things for some time already. Like after some layoffs in Intel, like it was, I don't know how long time ago, 1 year, 1.5, it just crashed, and we do not get access to anything. Just we can only rely on binary builds that are possibly made available on the resource and documentation center, or whatever it's called. So we basically rely on very poor changelogs with close to nothing information what has changed since last release, and just a binary, which sometimes has a debug variant, but sometimes also doesn't. So it is what it is.
Yeah, for some FSP, we can provide access. We can provide updates. For some, we can't. It's like wherever we can, we do it. Also, hacking FSP is not something we have to do often. So I would not treat it as an issue. Yeah, I guess like development environment for FSP is also something challenging. Could 3M query Intel after every Intel security advisor? We can, but what's the purpose of that? Like, if we want to lost all their, all the level of patience they have to for us, then yes, we can do this. But we don't want to abuse this relation.
Yes, the patience of our existence.
Yeah.
for our existence. Yeah, that's very. That's already like.
That's already scarce resource. I guess that's.
I would say this is already playing on the edge, right?
Yeah. We should have Wessel like 1 minute ago. So I guess we should switch to Wessel. So thank you, Michał, for that presentation. It was very informative. I guess like it can be used also by Wessel for some marketing, I hope, as well as the associated blog post. So Wessel, like please share your screen and you can start.